Hi everyone. So my name is Astha and I work as a machine learning engineer at Condé Nast.
Hey everyone, my name is Hari and I am a lead machine learning engineer at Condé Nast. So today we are here to talk about why you see what you like, machine learning in modern publishing. Hopefully, by the end of this presentation, you will know a little bit more about what Condé Nast is and what it does, what ML system consists of, and the general considerations when designing them. You will learn a little bit about how machine learning is done at our company and deep dive into some of our ML products. Towards the end, you will also get to solidify all this by thinking through the process of building an ML system with us. If Condé Nast doesn't ring a bell, have you heard of Vogue, The New Yorker, or GQ magazines? Then you have probably heard of us. So these are some of the brands in our portfolio. Condé Nast is an American mass media company founded in the 20th century. We are the parent company for a number of influential brands across various genres like food, travel, fashion, tech, and architecture. So these brands are present globally and cater to local markets. We have a large digital presence and a big audience base globally. To give you an idea of the scale at which we are operating, we have about 360 million monthly active viewers and are able to collect first-party data on their views, clicks, and other interactions when these users consume the content on our 108 brands that are spread across 32 markets worldwide. Now that you know about the company and what it does, let's talk about how a company like Condé Nast, which is in the publishing industry, uses machine learning. But before that, let's make sure that we are all on the same page about what an ML system is. So what is machine learning? Many people know that machine learning helps us learn patterns from data to make predictions. However, what many people don't know is for this to be actually be useful on a large scale, models don't live in isolation. So they live inside systems. So a machine learning system has multiple self-contained components that are responsible for the overall success of the system. The actual ML code that trains and scores the data is only a part of this system. In simpler terms, an ML system broadly consists of the data stack, which we use to store, manage, and process the data in a distributed manner. And then comes the modeling framework, which is the ML code that we just discussed about. Then the interface, which is used by multiple stakeholders such as data scientists, developers, and analysts to interact with the core functionality of the system. And then the software and the hardware infrastructure that this whole system is built and runs on. So each of the components I just described are designed around certain core principles that are shared with traditional software systems also. So the first is reliability, which is basically how tolerant your system is to things that could go wrong. Given that ML systems involve processing large amount of data and requests, we have the principle of scalability that helps to grow the system by replicating the overall process and architecture at scale. The world is constantly changing, so hence it's important to constantly update the features of the system to ensure that it can adapt as well. What makes a system adaptable is how flexible it is. So this is often achieved by making each part of the system self-contained or modular, so that multiple people can work on different parts at the same time. So given that these things change and we have multiple people working on it, it's also important for the system to be maintainable. And we just saw that ML system has many parts, right? So observability is how you can easily view the status of the different parts of the system. Now that we have talked about these systems in general, let's talk about machine learning at Condé Nast and how we use machine learning to generate revenue. I would like to let Astha walk you through the same.
Okay, cool. So let's start with how Condé Nast does machine learning. Broadly, our machine learning models can be classified into two categories. The first is content-based models. Content-based models rely on the metadata and text embeddings of our articles and recipes to recommend what to read next. We also have a big social media following, and this data is also used to predict which piece of content to post on social media based on what's trending. Next, we have audience-based models, which use first, second, and third-party user data to do things like ad targeting and targeted subscription marketing. The audience-based models feed off of the success of the content-based models, which increase the audience engagement, the growth, the revenue by driving traffic to our websites. So where can you see all these systems in action? Have you ever received an email newsletter from us? A lot of our newsletters rely on our personalization and recommendation models to provide you with things we think you may like to read next. Do you follow us on Twitter or Facebook? A lot of posts on social media platforms like Facebook and Twitter have been recommended by our in-house virality prediction model that tracks trends and recommends what to post next. Have you ever noticed the ads that pop up when you're reading? I'm sure most of us have encountered ads when reading content. So we have an in-house audience segmentation platform that helps us serve these ads to relevant audiences. Have you ever received a compelling subscription offer? We have a lot of propensity models that help our business tailor discount offers to different subscriber groups. So all of these are some projects that our team works on. So speaking of, who builds all of this? So we work on the data science and engineering team, and we are responsible for supporting the machine learning efforts of all the brands across the world. On our team, we have data scientists who are responsible for modeling, prototyping, and generating insights. And in addition to this, we also have machine learning engineers who are responsible for the other parts of the system. As you can see, our machine learning systems have multiple components that are not directly related to the model or the data itself. And so it takes a lot of work to actually go from proof of concept to a big production system. For the rest of this presentation, we will be focusing on the non-modeling components of the system. Before we dive deeper into some of our projects, we'd like to talk about another important part of machine learning engineering, which is the technology stack. Our technology stack can broadly be divided into the framework and languages that we use, the tools that we use for deployment and orchestration, and the platform that we use for storage and computation. Most of these tools are open source, but just because a tool is available does not mean that we should use it. And a large part of machine learning engineering is deciding which tools would be best suited to which project. So now that we have spoken about the technology stack, let's take a closer look at some of our machine learning products. As I said before, our models are broadly divided into content-based and audience-based. So we will pick one of each type to dive deeper into. Let me start with an audience-based approach. So earlier we spoke about audience segmentation and how we use it to serve relevant ads. So how do we serve relevant ads? Let's take a closer look at that product. So Spire is our in-house machine learning platform that performs this audience segmentation to help advertisers reach their target audience. For our purposes, audience segmentation is essentially the grouping of our readers across all our brands based on their interests. So segment in segmentation corresponds to like a trait or a group of traits. For example, whether a person is interested in fashion or technology or cars. So these are all traits that make up a segment. And grouping our audience in this way helps us serve relevant ads to our users. So before we go into the how, let's talk a little bit about the why. So why did we choose the audience segmentation approach? Surveys have found that 66% of consumers already know what they're going to buy or which brand they're going to buy before they begin a search. That's more than half of the people. And so if I'm a brand that wants to advertise my products, it would be really useful for me to know who is interested in my products beforehand so that I can target ads specifically to those people. And I may have a vague idea of what kind of people I'm interested in targeting. So for instance, I may know what kind of age group they belong to, what their gender is, what their interests are, etc. And so what would be really useful to me is if somebody has a large audience that has already been grouped into the categories that I'm interested in targeting. And that's where Spire comes in. So how does Spire work? Because of the scale and reach of Condé Nast, we have data from various online and offline sources and our brand portfolio about people's interests, their demographics, and their reading history. And we use this data to generate features and labels, where a label may be something like, oh, a person likes soup, or a person likes a specific pharmacy brand. But we have these labels for a very, very small percentage of our audience. And that's kind of where Spire comes in. So Spire essentially uses what we know about our audience to recommend to people, essentially and to recommend and to scale it to those who we don't know much about. And this helps create groups that our advertisers can target across multiple channels and multiple brands. So let's make this a little bit more concrete. For example, let's say we know that Hari likes smartphones and I like fashion. We are the target audience for the smartphone and the fashion segments. Spire can use this information about Hari and me, along with our reading activity and demographic information, to train a model to find people that are similar to us across all of Condé Nast's audience and brands. And Spire does this by having the model assign a score to every person in our audience, which represents the likelihood of them belonging to the smartphone segment or the fashion segment. And we also define a threshold. And if the user score is above that, we add them to the segment. It doesn't end there. So once we have this information, we can also combine segments. We can find the intersection of people who are interested in smartphones and in fashion. And this is how we use models to actually group our audience into these segments. However, as we mentioned before, models don't live in isolation. They live inside systems. So let's talk a little bit about how the system for Spire is set up and designed. So this is a simplified Spire pipeline. We have feature and label data, and that is joined together to produce a training data set through a process called assembly. This training data is then used to train and model, which is then used for inference to produce audience scores. And these scores are then consumed by various applications that we'll take a look at in a little bit. And they're also sent to our ad manager, which uses this input to decide which ads to show to someone. So earlier, we saw how we can build segments for people interested in fashion and technology and smartphones. But we have thousands of such things that we are interested in and that we'd like to build models for. And so that's one aspect of the scalability challenge with Spire. The question becomes, how do we model thousands of different segments? And one solution is to have one model per segment, in which case this pipeline that you see has to be repeated thousands of times. And so how do we manage this scale? All of this is kind of made possible by a very powerful internal abstraction that we call a workflow. For our purposes, and for those who don't know, an abstraction can be thought of as a way to generalize the most core and most relevant aspects of our data and our processes. As we mentioned previously, we have a model for each segment. And if we create a workflow for each segment, our design becomes very modular. And this modularity allows us to actually isolate the performance of each model associated with a segment and to further fine tune it. So what exactly does a workflow allow you to manage? A workflow, of course, knows what segment it corresponds to. It is also responsible for knowing how to walk itself down the pipeline that we just saw. So it knows how to assemble, train, and score itself. It also knows what data to use to do this and what model architecture to use when training. It also knows when to run each of these processes, and it maintains a log or a history of all the processes that it's ever run. We also use workflows to manage the metadata related to the execution of our processes. So for example, what cluster size to use, what machine type to use, etc. And since we have thousands of segments and hence thousands of workflows, we need to store all this information somewhere. That's where an object relational mapping or ORM comes in. Object relational mapping is a technique to convert data between different data type systems using object-oriented programming. In our case, it allows us to essentially create workflow objects and map them to rows in a relational database. For example, we may have a workflow class or a history class or a schedule class with attributes that map to different columns inside a database stored somewhere on the cloud. We can establish a connection to this database and easily create or modify workflows in an object-oriented manner. There are many open source libraries like SQL Alchemy and PsycopG2 that you can use to implement this in your own projects. So now that we have some idea as to how we have designed our system to manage the scale, let's go back to the pipeline and talk about each step in the process. So we use features and labels to create a training data set. And we do a series of pre-training checks to ensure that our data is not skewed to any one class. And there are a minimum number of positive and negative instances present. So one thing that we've learned is that we don't necessarily need all the data that we have to create a good model. And that's why we choose to actually downsample our training data set to reduce the computation cost. Another thing to be aware of is data drift, which is when the distribution of the input data changes. And we have some data validations in place to monitor this. So how does all of this run? We have software and infrastructure in place to actually support the process in general. So for instance, we use a relational database to store our metadata that I just described. Our process runs on a Spark platform. We use cloud storage to store our training data sets, and our process runs on a schedule that is managed by an orchestration framework. So our pipeline inherently has a lot of dependencies, and tracking all these different cascading effects can be very tricky. And that's why it's important to have visibility into each part of our pipeline so that we can effectively debug and maintain the health of the system. And so we've built a bunch of APIs and UIs to actually track this. So as we step through the pipeline, you will see a lot of these common infrastructural elements pop up. Next, we have our training data, which once we have our training data, we actually move on to creating the model. And there are many ways we can use, or many different modeling architectures rather, to model our different segments. And all of this can be managed using the workflow abstraction. For our machine learning framework, we have an internal library called Kalos. And one thing to note here is that this framework Kalos, which actually we have built on top of the Spark ML, is separate from its application Spire. And this allows us to independently develop both and to actually also allow Kalos to be reused by other projects. So similar to our data step, we also have infrastructure to support our processes and their monitoring. And the additional component to notice here is the machine learning framework, of course, but also the model registry or the tracking server, where we log our model training history and certain performance metrics, which we track over time. Once we have trained our model, it is time for deployment. In our case, this kind of involves running batch inference on a daily basis using our Spark platform. One thing to note is that we regularly retrain our models on a weekly basis, and 100% of the inference is done by the latest model. Additionally, our decision making for which user belongs to which segment is fully automated. And this means that the model makes 100% of the decisions. So you can see similar infrastructure elements at play here for the processing and the monitoring. So once we have a set of scores, it's actually time for these scores to be used by different applications and to be sent to the ad manager. One part of designing a machine learning system is kind of deciding what interfaces or applications to build and how to expose different parts of this system depending on the most common use cases. So for our more technical stakeholders who are interested in modifying or getting the status of the system, we have a CLI and an API. For the less technical stakeholders, we offer a dashboard and a website for them to better understand a single advertising campaign's performance and to create the segments that we just talked about. So hopefully you've learned a little bit about audience segmentation and the system that is needed to support it. Next, let's hear from Hari about a content-based model.
Yeah. So let's deep dive into another solution that you have built, Falcon, which is basically a social media manager's friend. So before we talk about the system, let's try and understand what prompted a solution like Falcon to be built. So every post that we see on social media looks pretty simple, as seen from this image, where we are merely redirecting to a content that is already published within our website. But in reality, creating a good social media post that can actually compel the audience to read the content takes a lot more time and effort than we think. So what goes into circulating a post on social media? First, the social manager has to analyze which topic is trending on the brand's website. Then all the content for that brand needs to be aggregated, both old as well as new articles that is related to this trending topic. Once the aggregation part is completed, the manager takes a call on the best post to be circulated on social media. And finally comes the post curation, which includes a summary of the content through a concisely written caption and also a catchy image to go with it. So this was all done manually by the social media managers, making the frequency of posts that were being made and the relevance of them a bit challenging. So this challenge raised a question. What if there was a tool that can work along with the social media managers and help them to discover trending content within their sites? Recommend content, especially older ones, to promote on social platforms based on data. And then provides a suite of customization options for the brands to alter things like the number of recommendations that they might get and filtering out specific sections or filtering out specific authors and so on and so forth. And finally, to also fit into the current social workflow, which the social managers are comfortable with. So this would result in improving the traffic coming in through these social platforms, thereby increasing the overall audience engagement and also better content discovery across the site. So these are the use cases that paved the way for Falcon to be built and integrated into a brand's workflow. So let's look at what Falcon does through a small example. Condé Nast Traveler India, also called CNT India, is a luxury, lifestyle and travel magazine which is published by Condé Nast and specifically caters to the India market. Let's assume CNT India has been recently receiving more traffic towards content related to food and signature dishes in India. So this trend in traffic is observed by the Falcon system, which aggregates all things related to food within the brand. An ML model scores them and recommends a set of content that can be posted on the social media page, which would interest the followers of this brand on those platforms. So how does Falcon actually work? So Falcon makes use of a variety of data from different systems. So it uses traffic data to see trends in virality. It uses content data and then also the social poster data, which is nothing but the history of all contents that have been posted on the social pages. So we build features for the model using this data, and this model predicts which is the optimal content that can be posted on the channels based on the last few hours of traffic. So these predictions are then pushed to the social media platform optimization tool, which is used to manage all the social posts. Then the social media manager logs onto this platform, reviews the recommendations made by Falcon that is available on their queue, and decides whether to post it or not. So if the recommendation is relevant to the trend and gets a nod from the manager, it is shared to the social media pages through the tool itself. If it is not, then the manager has options to either optimize the recommendation or just leave it on the queue, which then gets expired after a pre-configured shelf life. A social media manager can also provide feedback to Falcon about the recommendations that are being made, which the system uses to tailor its future recommendations. It is really important to have mechanisms in place to track the effectiveness of the systems on a regular basis. So let's just look at how Falcon tracks it. To track effectiveness, we make use of clickstream data on the brand website for the social posts that were being made using the optimization tool. We do this to understand how many clicks have been made on each content that are recommended by Falcon. Using this, we calculate custom business metrics like the total number of Falcon recommendations that have been made and that have been posted and the click-through rate on these posts. So these metrics are made available in a dashboard, which acts as the source of truth for tracking Falcon's performance. We use this dashboard for monitoring, and if we notice a downturn in the clicks of Falcon recommended posts, we reach out to the social media manager of that particular brand to understand the root cause and probably retrain our models. So what is actually powering this system in general? So for developing Falcon, we use Python as the preferred programming language for the core framework. And the data processing is done in a distributed manner using the Spark framework. So with regards to the data that we are using, so content and traffic data are gathered from our internal systems and we store it on cloud. Social data is collected through the optimization platform, and that's also stored on the cloud. So using this data, like what model infrastructure is being used? So models are trained again over our Spark distribution platform, and the choice of the modeling algorithm and the framework that we are choosing is dependent based on the available data points. Our infrastructure can also support multi-model testing directly in the production environment to enable testing new approaches and results. So this is powered by a relational database table that tracks all experiments in the tracking server and its associated versions. So we talked about customizations earlier, right, at a brand level. So how are these handled? So customizations such as the nature of recommendation, like whether the recommendation is an article or a gallery or a review, etc., are enabled using different parameters that are maintained on relational tables, which can be easily updated. And these configs are managed by an access restricted user interface that is capable of logging any change that has been made into the configurations, and along with the information about who has made this change. So this is really important for us to debug any issues that might come up. And what is the cadence of this recommendation and how is this recommendation being served? So the recommendation cadence is hourly for all the brands that we have onboarded, and output from these hourly scoring process is sent to the optimization tool through the tool exposed APIs. So we also store a copy of these hourly recommendations on our cloud storage for future reference or analysis. So with all this, like how are we managing the orchestration and the resourcing needs for these continuous running pipelines? So the orchestration is handled by an orchestration framework, which is backed by a relational table as well. So to balance the load on our Spark framework as well as the orchestration framework, our pipelines run on a dynamic schedule powered by custom built cursors. So these cursors allow us to schedule the inference in a round robin manner for all the brands. So let's look at some Falcon highlights. So Falcon is a prime example of a human AI collaboration wherein both parties have their defined roles and work together to achieve a common goal. The AI handles its area of expertise with regards to analyzing the data and making predictions, whereas the human in the picture plays to their area of expertise, which is domain knowledge. Falcon right now services 39 brands across 9 markets by churning out hourly recommendations. So we have also plans in place to onboard Falcon into the social workflow for more Condé Nast brands that have a good audience base. A system with a scale such as this and running every hour for all the brands should have a good modularized code to ensure that core system values we talked about earlier, such as scalability and adaptability, are in place. So through proper coding guidelines and the principles that we follow, Falcon can extend its service to new markets and brands in less than 2 days once the model has been served, with very minimal modifications to the code and to the setup. In terms of maintainability and servicing brands requests, we have a support team set up that acts as the first line of defense for any production related issues or any brand level request that comes in. Okay, now that you have seen how machine learning is used in a publishing company, it's time to apply it. Let's build a system that gives personalized newsletter recommendations. But before we start, let's break this prompt down a little bit. So what is a newsletter? Newsletters are nothing but an email to a subscriber with recommendations for what to read. Condé sends out so many newsletters to its newsletter subscribers across various brands. Let's also talk about what personalized recommendations are now. So most people probably know that recommendation involves presenting some options that are selected on the basis of criteria. And personalization involves meeting the unique requirements of individual readers. So when put together, they allow us to tailor the reading experience of our users.
Now that we've talked a bit about the problem conceptually, it's time to actually build the system. So a lot of people have probably seen this diagram. It represents a general machine learning pipeline. And we will be following it to talk about the different decisions, trade-offs, and considerations at each step of this process for this particular problem. So let's start with scoping or defining the problem in more details. So what problem is the system going to solve? So let's forget the newsletter part for a second. Fundamentally, we need to personalize the recommendations for each of our subscribers. And what do we care about most when solving this problem? At a business level, we probably want people to click on recommendations. And we care about this because we want to increase the audience engagement or the click-through rate so that it can essentially increase the amount of traffic to our websites from these recommendations. So how will we create a system that can actually do this? So let's move along the pipeline to find out.
Okay, let's talk about data first. So what data will we use? Where will it come from? And what pre-processing we need to do on top of it? Since we are trying to provide recommendations for what to read, it would be useful to know what each user has read in the past. So luckily we have a feature store which has this information, but we may have to do some additional feature engineering on top, but that falls under the domain of data scientists. So another thing to keep in mind is that the labels should be consistent across various runs. Let's keep it simple and have it binary for this use case, like whether the article has been read or not read. Once we have standardized our inputs, then we can move on to data validations, which involves tracking changes in distributions of our features and labels, along with some data quality checks. Next comes decision on storage. So what should we be storing? We should store our training data set, or at least the metadata. The reason this is important is reproducibility. So it's important to be able to reproduce runs, as this helps us backtrack and explain different recommendations that are produced by the model. We could also store the metrics and the logs associated with running the pre-processing. And finally, abstraction. If our pre-processing is just a series of steps and we don't need to manage the state of the objects, we probably don't need a class. So it can just be a process. One last thing to mention is that it's important to preserve the privacy of our users and make sure that we are dealing with anonymized data at each step, which doesn't have any personally identifiable information.
Once we have our data, it is time to actually make decisions about how we will do training. So in general, the modeling part involves the machine learning framework or the algorithm, the hyperparameters, and the data itself. So let's start with the data. How much data do we actually need to build this model? And this is usually left up to the to the data scientists to actually decide. And it could actually change over time. So we may start with a model that uses 6 months worth of data, but we may want to move on to 3 months or even a few weeks. And our process should be able to adapt to different time windows that we may choose. The modeling framework is again left up to the data scientists to choose, but we need to decide whether we will store the model in a model registry or a tracking server or on the cloud. And our design to manage all of this should be flexible enough that it supports experimentation by the data scientists so that they can improve the models, but it should also be suitable for production. And since we have to manage the state of our hyperparameters and the configuration for many different brands who possibly want to use the service, we could consider using a class or a more object-oriented approach here. Some other things to consider are retraining and model selection. For now, let's assume that we will retrain our model right before inference, but over time we may change our strategy to be more performance-based instead of recency-based. In general, in the industry, we follow a more data-centric approach to machine learning and not a model-centric approach. And this means that if we have to improve the performance of our model at any point, we will focus more so on improving the data and not necessarily using more complex modeling architectures. And this is because of, firstly, garbage in, garbage out, right? This is the basic software engineering principle. And also model explainability. We should be able to explain the outputs, our recommendations that our model is producing.
Okay, next to talk about the deployment part. So what we need to be concerned about is how we will productionize this model to consistently recommend articles. One thing to think about this is the frequency of inference. So the inference for our use case here does not have to be in real time. So recommendations need to be made right before we send the newsletter, so that we have the most up-to-date information of the user preference as well as the most recent batch of articles that we can recommend. So in our case, we have to align with the business needs. So let's say we need to send the newsletters every week. So we will run our inference every week as well. So one other thing that's important in real life systems are cost. This involves choosing what type of machines to use and the optimal number of machines, etc. So this consideration should be applied to other parts of the system as well, and not just to the deployment. So now we have a blueprint. Are we done? No.
So now that we've laid out the basics of our system, let's see how we can tie it to the core principles that we talked about earlier in the presentation. So let's start with reliability. What happens if the system fails to produce recommendations? And this can happen in the real world due to many different things, such as orchestration issues, resource issues, upstream data issues, etc. However, our newsletter should still go out in time. And so to make sure that the system is reliable, we could actually come up with some fallback strategies to use. For example, if there are upstream data issues, we could look at the previous week's recommendations and choose the top ones that we didn't send out last time. We could also send the most trending or the most popular articles. To manage orchestration and resource issues, we could have automated retries built into our process and have live notifications to maybe a dedicated support team so that they can be dealt with quickly. Next, let's talk about observability. Some of the tools we use come with their own dashboards, and we can use those to monitor the health of those components. But observability is also an iterative process. Only once we deploy will we have a better idea of what can go wrong with this system. And then we can come up with ways to track those things. And so, again, it's iterative. And observability also involves looking at model performance metrics and also more downstream business metrics. So for example, we may want to look at like how many people are actually clicking on the recommendations that we are sending in our emails. Next, let's talk about scalability, adaptability, and modularity. And these kind of go hand in hand for our project. So accounting for these kind of starts at the code level, where we need to design generalized abstractions whose implementations can be easily swapped without changing the public interface. Lastly, let's talk about maintainability. This involves setting up logging at various levels in our code, having good documentation, code review, and following style guidelines.
Okay, so what are the next steps? So systems keep changing and there are challenges that can come up with that. So for instance, we may have to evolve our newsletter platform to support multiple languages and brands across the world. So we may also need to change or run A/B tests and experiments to prove the efficacy of our approach. So there is also continuous dev and iterations that are happening when maintaining an ML system. So this involves both top-down as well as bottom-up efforts to narrow down exactly on what to improve. Additionally, it involves setting up automated integration, deployment pipelines, unit tests, and integration tests. We should ideally also have a separate development and staging environments to ensure that the updates being made don't break the system in production. Finally, all of this definitely involves global collaboration. So it's essential that our systems can be developed and understood by everyone involved.
That was a lot. So what are the main takeaways? So overall, machine learning models can help publishing companies like Condé Nast stay relevant in today's digital era. One of the main takeaways should be that model is not the machine learning system. It's only the beginning. Keeping in mind core principles we talked about, like scalability, maintainability, etc., can really help us ensure that our system can be developed and supported properly. So data scientists and machine learning engineers work together on a project, but it's important to segregate the roles of each for efficiency. Good abstractions and modularization can really help us scale our products and develop them with others. Iteration. So of course, no system is perfect, and we should always prioritize between the must-haves and the good-to-haves. What gets measured gets managed. In order to maintain and operate our systems effectively, we need to be able to observe them and track things that can go wrong. Lastly, one hat does not fit all. We saw a lot of systems and they were not the same. The tech stack and the infrastructure should be chosen according to the project's unique needs. Hopefully, all of that was informative and you can take some of these learnings and apply them to your own projects. We will now open it up to questions.
So we have a question from Agamdeep Singh on, does optimizing individual models in the modular workflow always result in global optimization also? Any expectations to that?
So that's a great question. And it kind of depends on what you mean by global optimization. But in general, by improving each of our models individually, hopefully we produce better overall segments that kind of translate over to like all the different segments that we have. And so it's basically the small things make up the big thing, right? So yeah.